Welcome back, design junkies, to Mechanical Engineering Made Simple. Today, we're doing a deep dive into the literal and often unseen physics that govern how almost everything is made. If you've ever wondered how a huge batch of, say, pharmaceutical powder or a vat of polymer can be identical every single time, well, that's the core challenge of mixing engineering.
It really is. We've pulled our material today from some advanced handbooks on the topic, and we're going to get into blending, sampling, heat transfer, and even chemical reactions.
And the big picture here is that mixing sounds simple, but it's not.
Not at all. Achieving true molecular level homogeneity. That's where the physics gets incredibly complex. The real headache for engineers is making sure that what worked in a small lab beaker still works in a massive silo every single time.
Okay, so let's unpack that, starting with what seems simplest. Mixing dry powders, you've got these theoretical states of what a mixture can be, and honestly, a couple of them are pretty counterintuitive.
Right. The first one is purely theoretical. It's called the perfect mixture.
Like a crystal lattice.
Exactly. Imagine particles alternating perfectly, one of A, one of B, and so on. Every single sample you could possibly take would be identical. But, unless you're placing each particle by hand, you're never going to get there.
So the best we can actually hope for is what's called a random mixture.
That's the practical goal for most free-flowing powders. It's purely statistical. The particle here doesn't care if its neighbor is the same or different. You end up using a binomial distribution to describe the quality.
But then there's this third state, the ordered mixture, which can actually be better than random. How does that work? If random is the best statistical average, how can non-random be an improvement?
Because the physics changes. This happens in cohesive systems where surface forces take over. Think of very fine, small guest particles, literally coating larger host particles.
Oh, so they're stuck together.
Precisely. The unit you're actually mixing is no longer particle A and particle B, it's this new composite, this coated host particle. And since that unit is uniform, you're just mixing a collection of identical things.
So your samples become incredibly consistent.
They can be even more homogeneous than a perfect random mix of the original components would allow.
That sounds amazing. So why isn't every fine chemical blend made this way? What's the catch?
The catch is that it relies on those surface forces being stable. It works great on a small scale. But when you scale up to industrial equipment, the huge shear forces just rip those bonds apart, and the whole thing can collapse back into a segregated mess.
Segregation. Okay, so even if we get a great blend, the next hurdle is just figuring out what we have. This is the sampling trap, right?
It's the Achilles heel of solids blending. You can't see inside the mixer, and powders just love to demix on their own. So you have to rely on sampling, and almost every tool you use introduces some kind of bias.
Let's talk about the thief samplers. I was shocked at how flawed the standard side sampling thief is.
It's a huge problem. You stick it in, a slot opens, and powder flows in. But first, just putting it in disturbs the bed. And second, it relies on passive flow.
Meaning the easy-flowing stuff gets overrepresented.
Exactly. The smallest, most free-flowing particles just pour right in. Your sample might be almost entirely the fine component, which is completely wrong.
And the fix for that, the unsampling thief, just created a different problem.
It did. It forces material in as you push, which reduces that flow bias. But the tool itself is bulkier, so it disturbs and entrains even more material on the way down. You're often just creating one error for another, and it frequently makes the mixture look better than it actually is.
So for a real accurate picture, you need a core sampler.
That's as close to a gold standard as we get. It pulls out a continuous, unbroken core of material. It minimizes all those disturbances and lets you see the differences between layers.
Which is why you can't just rely on an average concentration for the whole batch.
No, an average tells you nothing about where the problem is. We use axial variance to see differences between, say, the front and back of the blender. And then radial variance tells you about the consistency within one of those locations. You need both to diagnose what's going wrong.
The way these grains flow, it feels so different from fluids. You said they have to dilate.
Yeah, that's the key. Liquids can just shear smoothly. But for a pile of grains to flow, the individual particles have to physically move apart a little to expand. They have to dilate.
So you can have different states of matter all at once.
In a way, yes. You can have a static, solid-like region sitting right next to a flowing, fluid-like region, and maybe even a gas-like region near the surface. It's so complex that our computational models for granular flow are still way behind fluid dynamics.
And that complexity leads to two main types of equipment, tumbling blenders.
Right. Things like V blenders, they rely on gravity. The mixing really only happens on the top surface as it tumbles. They're gentle, but fines can easily segregate into a core in the middle.
Versus convective blenders, which are more aggressive.
Much more. A ribbon blender, for example, uses an impeller to physically move material all over the place. It's great at fighting segregation, but all that action creates high shear.
Which can grind your particles down or create a lot of heat.
Exactly. It's always a trade-off.
Okay, let's make that transition now from dry powders to, well, the really heavy sticky stuff. Viscous fluids. We're talking pastes, polymers, things over 10 Pascal seconds.
And suddenly, all the rules change. You completely lose the gift of turbulence.
No more eddies to do the work for you.
None. And molecular diffusion is incredibly slow. So all your mixing, 100% of it, has to come from direct mechanical action. You are physically forcing it to mix.
And this forces engineers to think about two very different kinds of mixing.
That's the key distinction. First, you have distributive mixing. It's all about spatial uniformity. You stretch and fold the fluid, creating thinner and thinner layers like a baker folding dough. You're just trying to spread everything out.
And the other is dispersive mixing.
That's the intensive part. It's about applying high mechanical stress to break things up, lumps, agglomerates, droplets of another liquid. It's the brute force.
So you need both. You need to break the lumps, and then you need to spread the pieces.
Almost always, yes. You need intensive dispersion and extensive distribution.
What I found really wild in the material was this hard limit when you're mixing two immiscible fluids, the viscosity ratio.
It's a fundamental physical barrier. If the viscosity of the droplet you're trying to break up is about 4 times higher than the surrounding fluid,
More?
or more, simple shear flow cannot break it. It's physically impossible. The forces just aren't there.
Wait, so no matter how fast I spin my mixer, if the oil I'm adding is just a bit too thick, the droplets will never break up.
Not with simple shear. You hit a wall. To get past that, the mixer has to generate what we call elongational flow, a true stretching and pulling action. It requires very different specialized equipment design.
All this mechanical work, forcing things to stretch and shear, that creates a massive heat problem, doesn't it?
A huge one. It's the double-edged sword. All that power you put in becomes heat through viscous dissipation. And at the same time, these thick fluids are terrible at transferring that heat out through the vessel walls.
So you have a machine that's great at making heat and a fluid that's terrible at getting rid of it.
Exactly. And here's the paradox you have to remember. If you think, I'll just speed up the agitator to mix better and improve heat transfer, you could actually make things worse.
How?
Because the power you're adding goes up exponentially with speed, dumping in way more heat. But the improvement in the heat transfer coefficient is modest at best. You can get to a point where spinning faster actually just cooks your product faster.
Wow. So there's an optimal speed for cooling, and going past it is counterproductive.
There is. It's a critical constraint. It's why you see specialized equipment like helical ribbons that have very small clearances to the wall. They have to physically scrape the fluid off the wall to force heat transfer and make sure nothing stagnates.
And that heat problem is the main reason for the scale-up dilemma, right? Why bigger mixers run slower.
It's the absolute driving force. When you go from a small reactor to a huge one, your volume increases much faster than your surface area for cooling. So to avoid scorching the product on the walls, you have to slow down the blades and reduce the power per unit volume.
Which means mixing takes longer on the large scale.
Significantly longer. You trade time for thermal safety.
Okay, finally, let's connect this to chemistry. We're talking about mixing sensitive reactions. This isn't just about being uniform anymore. It can determine if you make the right product at all.
Absolutely. This is common in pharma and specialty chemicals. A reaction is mixing sensitive if it's so fast that it starts to happen before your reagents are even fully mixed at the molecular level. We call that micromixing.
So the molecules are reacting with whatever's closest, not necessarily what they're supposed to. What does that do to the final product?
It can be catastrophic for your selectivity. If reagent A and B are supposed to react, but you have a local spot with not enough A, then B might start reacting with itself or decomposing. Your yield of the desired product just plummets.
And this isn't just for liquids. The same problem happens in multi-phase systems because of mass transfer limits.
Right. There's a classic example with an antibiotic synthesis. The reaction creates hydrochloric acid as a byproduct, which is toxic to the main product.
So you have to get it away fast.
Instantly. Even if the overall pH in the reactor is fine, the local concentration of HCl right at the surface of the particle can be high enough to destroy the product as it's being made. The solution wasn't just to stir harder.
What was it?
It was a more elegant solution, using things like powdered molecular sieves that could get in there and scavenge the HCl locally, right where it was formed, before it did any damage.
That leads us to what you said is one of the hardest operations to scale, crystallization.
Because mixing affects everything. Take nucleation, the creation of new crystals. It's highly dependent on impacts, either crystal on crystal or crystal on impeller. If you mix too hard, you get way too many nuclei.
And that's bad because
Because the final crystal size you can achieve is exponentially related to how many nuclei you start with. Too many nuclei means you end up with tiny, fine powder instead of the large crystals you wanted.
it sounds like you're trying to juggle glass balls. You need to move them around for them to grow, but you can't let them hit each other too hard.
That is the perfect analogy. It's the ultimate trade-off. You need enough circulation for mass transfer and to blend everything, but you need low enough shear to prevent overnucleation and breakage. Nailing that balance is everything.
And just quickly, how do continuous mixers handle this? They have a different problem, right? Feed fluctuations.
They do. They use what's called axial mixing to smooth out or dampen any variance in the feed streams. It's measured by something called the variance reduction ratio, or VRR.
But high axial mixing has a downside.
A big one. It broadens the residence time distribution. That means some particles fly right through the mixer while others hang around for a long time. If the mixer is also a dryer or a reactor, that's a disaster. Some product is underprocessed and some is overprocessed.
So when we put all this together, the real art here is so much more than just stirring something in a pot.
Oh, it's about controlling things at a molecular level, managing these brutal thermal constraints, and balancing these delicate, conflicting requirements, especially in sensitive processes like crystallization. It's a field where, honestly, experience and testing still rule because the models just aren't all the way there yet.
It really changes how you think about the word blending. If knowledge is power, then industrial blending is the ultimate power application. Considering that increasing the agitator speed to mix a viscous fluid faster might actually prevent you from cooling it, where else in your world do your solutions inadvertently become part of the problem? We'll leave you with that thought for the week. Until next time, keep digging deeper.